Hello folks, Mr. Long here. We're just going to go over or have a brief screencast of the algebra of logs, or introducing some of the algebra of logs. What I want to do is examine the logarithm as the inverse function. So if you have y equals b to the x, then the inverse of that, we know if you interchange x and y, right, you get the inverse. And so the inverse of y equals b to the x is x equals b to the y, which does make sense. But from what we've already learned about implicit and explicit relations, it doesn't make a lot of sense to have an equation in this form. We like our equations to be y equals. So what we do is we take this form, x equals b to the y, and we rewrite it as the logarithm is equal to, or y equals the logarithm of x to the base b. Okay, so where y is the exponent, right? So look right there, y is the exponent. B is the base. You can see the base there and the base there. And then x is what we call the evaluated power. So that's the answer for the exponential part, right? So again, y is the exponent, or what we call the logarithm. B is the base, and x is the evaluated power. And that way we have this form right here, the inverse of the exponential form, into an explicit relation. So y equals. Okay, so just simple stuff where we create the inverse. So let's see here. So for this one, y equals 3 to the x. I need to switch x and y and write it as a log. So y would equal a logarithm of x to the base b. Oh, whoops. And our base b in this case is actually 3. Okay, it's a base 3 logarithm. Alright, so for this one, I'm doing the inverse of this, and again, my base is going to be 4. So I want to, the inverse of the logarithm is the regular exponential function. This is going to be y equals 4 to the x. Okay, that's the inverse of the logarithm. Okay, so just that's very straightforward there, just writing the inverse. Sometimes it'll just say, the question will say express in logarithmic form, or it'll say given this exponential form, express in logarithms. And that would be this kind of question, right? Another one might be given the logarithmic form, express as the equivalent exponential relationship. Okay, and so that would be how things work. Okay, let's look at composition of inverses. So now that we know the way things are written, we're going to look at the composition of inverses. And so as our example, just to go through this, let's start with f of x equals root x, and the inverse of that, of course, is x squared. I think we know that. So if I was to do a composition of this, we start with our outside bracket, f, and then write it as an open bracket. So our outside bracket would be square root, and then inside the bracket, I don't think I need a bracket that big, do I? And then inside the bracket would be square root, sorry ladies and gentlemen, inside that would be the inverse, which is going to be 5 squared. Well, that just gives us the square root of 25, which is just 5. So we notice that when I do, we did composition of inverses in the last unit, and we just found that the answer was always x, so what you started with. So notice 5 is substituted in, I end up with 5. Similarly, I've got another one here, so square root of 7 squared would equal the square root of 49, which in turn equals 7. Okay, so when I compose a function with its inverse, I always get just x, what I started with. Okay, the composition of an inverse. So specifically, so if I look at this, f of f to the minus 1 of 5 has to be just 5. F of f to the minus 1 of 7 has to be just 7. how does this connect to logarithms? Well, we know that there's a function and there's the inverse of that function. So if this is a function, the exponential function, this is the inverse. We also know this, we got this result from the last time, that every time I take the inverse, my final answer is just the number that I started with. Okay, the final answer is just the number I started with. So what I'm going to do here is write the function composition where I take the outside as f, the inside as f inverse. So that means 2 to the x goes on the outside. So I have 2, and then there's an x here, right? But I leave an open bracket. What do I replace that with? I replace it with the inverse. The inverse is this, log of x to the base 2. Well, we know that that has to be worth just x, right? Because I've done a composition of a function and its inverse. Okay, I know that's not the most intuitive thing, but still we need to do that. We need to examine that and understand that the composition of inverses results in just the value of x. Okay, so if we take this right here as a question, so let's do the composition of f, and then the inside function is f inverse at 8. So what this looks like is 2 to the log of 8 to the base 2. Well, what's this worth? What exponent do I put on 2 to get 8? What exponent do I put on 2 to get 8? Well, it's 3. So I can call that 2 to the 3, and that's just 8. Well, again, I started with 8 here. I did an inverse composition here, and I ended up with the number that I started with. Okay? So here's an example right here. I have 4 and I have 4. So 4 is a base in an exponential relationship. The composition is the inverse with base 4. So what does that equal? It equals 16. Okay, can I do that in long form just to prove it? Sure. I know what this is worth. Log of 16 to the base 4 is 2. So that's 4 to the 2, which equals 16. But I could have written 16 directly because I'm doing an inverse composition. And here's one that looks really hard but isn't. 1/2, 1/2. The bases are the same, and I'm doing an inverse composition. So automatically the answer is just 7. Here's one that is much trickier. I've got a 9 here and a 3 here. And so right now, those are not inverses because they don't have the same bases. So what I do is I change 9 to base 3. Okay, I change 9 to base 3. Now it still doesn't look right because I've got this 2 out front. But due to the commutative nature of multiplication, in other words, 2 times 3 equals 6, and 3 times 2 equals 6, I can take this 2 and move it to the back of this. So I end up with 3 to the logarithm of 10 to the base 3. And so what I can do is all of that, so that's being, the 2 comes at the back. And that just becomes, because I put the 2 at the back, it becomes a power of a power, right? And so we know that the answer for this portion right here is just 10 because I've got a 3 and a 3. So that's just a composition of an inverse. Log of 10 to the base 3 as the exponent on 3. So that equals, I'll put this part here. This part here in blue just equals 10, and then I've got squared, and that equals 100. Okay? So when you see unlike bases in this scenario, unlike base between the base here and the base in the logarithm, in a composition, you have to get a common base and then change the order of multiplication, which you're allowed to do. Okay, folks? So let's do just really quickly, number 3, solving simple log equations. This is going to require rearranging into the exponential form. So if you look at this one, your base is 2, your exponent is 3, right? That's your exponent. The logarithm is the exponent. Base is 2, logarithm is 3. The goal here, by the way, is to isolate this value right here, the evaluated power. So we can do that by writing it as base is 2, exponent is 3, and that equals x. Well, 2 to the 3 equals 8. Therefore, 8 equals x. Okay, so just one question. And let's see here. Oh, this is something called the common logarithm. You're going to notice something. There is no base symbol there. When there is not a base symbol showing, it's automatically accepted that it's base 10. 10 is the most common logarithm that's used. Okay, and they call it the common logarithm. And it's sort of like, you know how when you do a square root, you don't put the 2, right? You don't put that 2 there. But for a cube root, you do. Right? So you don't see the 2 there. So that's more like the common root, right? The common root is the square root. It's no different with logs. Okay, so how do we do this? I need to isolate x minus 3. My base is 10, my exponent is 2. 10 to the 2 equals x minus 3. 100 equals x minus 3. I add 3, and I get x equals 103. Okay, so now once you've done that, you're going to be able to do the homework, which you'll see recorded in the tiles. Hope you have a great day.